and today I'm gonna present my work named SequenceMatch, revisiting the design of with strong augmentation for semi-supervised learning. So first of all, let's revise what is semi-supervised learning. So semi-supervised learning contains of two phases. The first phase is training the model on limited with augmented label data under supervised manner. Then we continuously create weakly and strongly augmented and labeled data and feed them through the train model to get the prediction, and the weak prediction will be used at the pseudo label to train for the strongly augmented prediction, and this process repeats several times. However, due to the usage of the high threshold, the semi-supervised learning model is easily overfitted to the small label training datasets and produce overconfident, incorrect prediction. This is because of the confirmation bias, and it produces the high divergence between the strong and weak prediction. So to mitigate the problem of confirmation bias and high Kullback-Leibler divergence, we separating the high confident and low confident prediction and process them separately. For high confidence prediction, we adding the Kullback-Leibler losses to encourage the consistency between three different augmented prediction, which we call the weak augmentation, medium augmentation, and strong augmentation. And for the low confidence prediction, we sharpening the weak and strong prediction before using the cross entropy loss. So by sharpening the prediction, we can reduce the confirmation bias and overfitting on them. So here is the supervised lot. The supervised lot is normal at the conventional method. And for the unsupervised lot, we adding the extra cross entropy loss between the low confident prediction, and for the high confident prediction, we adding the Kullback-Leibler divergence. So we can, by reducing those divergence, we encourage the consistency between three different predictions. Previous work suggest the remix match, introduce K-strong augmented version and calculate the loss between them, which causes a large overhead for computation and memory consumption, as we show in the left figure. And CoreMatch had the same approach as ours. However, they used the two strong augmentation and forcing the contrasty learning between those two strong prediction. This gives the high discrepancy between the prediction, as they will be very different. Difference with them, we use the weak augmentation, medium augmentation, and strong augmentation, and forcing the consistency between the prediction. So ours giving less overhead than previous method. And we benchmark our method on the small datasets such as the Cypher 10, Cypher 100, SVHN, and SCL10 on different number of label. And we can see that our method SequenceMatch consistently outperform the previous work, and the current SOTA suggests the free match and flex match. And also we benchmark our method on the larger dataset such as the ImageNet under two different schemes, the 100K number of label and 10% of label. And we can see that SequenceMatch outperform the current SOTA, which is SimMatch and FreeMatch, with the large margin under both training scheme. And here we showing the accuracy and loss on the ImageNet between fixed match, flex match, and sequence match by the iteration. And as we can see that the sequence match converges faster than the both of the fixed match and flex match. And we also measure the expected calibration errors on the ImageNet between the fixed match, flex match, and sequence match. As we can see, sequence match has much lower ECE than the previous method, and this suggests that our method is less biased than the others. Thank you for listening.